What if the numbers you learned in school, those seemingly simple digits and symbols, had a secret life, a hidden existence beyond the equations and formulas? What if they were keys to unlocking realities we can barely imagine? In this video, we'll trace their journey from the familiar 2D complex plane into the fascinating world of four-dimensional space, where geometry bends and reality expands. Stay with us, and if you're passionate about math, imagination, or discovery, don't forget to like, share, subscribe, and leave a comment to share what most amazed you. The number line, that familiar straight line stretching infinitely in both directions, is just a single thread in a vast, multi-dimensional tapestry. A tapestry woven with numbers, shapes, and dimensions beyond our everyday perception. Complex numbers, those intriguing combinations of real and imaginary parts, are usually represented as points on a flat, two-dimensional surface. A plane where every point corresponds to a unique complex number. Real and imaginary parts plotted on a graph, neatly organized and easily visualized. But what if that surface, that seemingly simple plane, is just a shadow of something richer, a mere projection of a more complex reality, living in four dimensions? A world where our familiar rules of space and geometry bend and twist in unimaginable ways. Mathematics lets us peek into these higher realms, offering us glimpses beyond our limited senses, describing them with precision even if we can't see them, allowing us to explore the unseen corners of the mathematical universe. Our quest to glimpse what it means to see in four dimensions, to grasp the essence of hyperdimensional space, starting from the familiar 2D complex plane and building up layer by layer, dimension by dimension. We'll use analogies and shadows, visual metaphors to bridge the gap between our three-dimensional intuition and the abstract world of higher dimensions, to stretch our minds beyond the limits of perception, to expand our understanding of what is possible in the realm of mathematics. By the end, you'll have felt the shadow, the faint impression of a four-dimensional world pass through your mind, a fleeting glimpse into a space beyond our everyday experience, forever changing how you see numbers in space, and opening your mind to the infinite possibilities that lie hidden within the fabric of mathematics. Let's start with the complex plane. It's our initial window into the world of complex numbers, a foundation upon which we'll build more intricate understandings. This plane is essentially a graph with a real axis, representing the real component of a number, and an imaginary axis representing the imaginary component. It's often referred to as the Argand plane. Numbers like 3 plus 4i, which combine both real and imaginary parts, become points on this plane. Each complex number finds its unique location. For example, 3 plus 4i is located 3 units along the real axis, and then 4 units up the imaginary axis. This gives us a clear visual representation. This Argand plane beautifully transforms algebra into geometry, allowing us to visualize algebraic concepts in a spatial context. A fascinating property is that multiplying by I rotates a point 90 degrees counterclockwise around the origin. This simple operation has profound implications. It's a powerful tool, foundational in engineering and physics, used extensively in areas like signal processing and quantum mechanics. But this convenient 2D map is just a flattened version of a much larger reality, a projection that simplifies a more complex structure. It's like a world map distorts the globe, sacrificing accuracy to fit a three-dimensional object onto a two-dimensional surface. The complex plane shows us one aspect of complex numbers, a particular slice or perspective, but it also hides a deeper multidimensional truth, a richer structure that extends beyond our immediate perception. What if we add more axes? What happens when we move beyond the familiar two dimensions? What about numbers that need 3, 4, or even more dimensions to be fully represented? The possibilities are endless. To go further, we need new ways of thinking to break free from the constraints of our two-dimensional intuition. We need new metaphors to guide us into the unseen, to explore the mathematical landscapes that lie beyond our current understanding. Before tackling 4 dimensions, let's jump from 2 to 3. Imagine flatland, a world of 2D beings with no concept of up. If a 3D sphere passes through their world, they see a point appear, grow into a circle, then shrink and vanish. To them, it's magic, a cross-section of a higher reality. We're like flatlanders when it comes to the 4th dimension, only able to perceive 3D slices of 4D objects. If a hypersphere passed through our space, we'd see a sphere appear, grow, then disappear. Cross-sections let us translate 4D phenomena into sequences of 3D events. This is our first tool for visualizing the impossible. Another tool for understanding higher dimensions is projection. Shadows. A 3D object casts a 2D shadow. We lose depth but learn about the original. Imagine a 4D object casting a 3D shadow into our world. The 3D shadow of a tesseract, a hypercube, looks like a cube within a cube, morphing as it rotates in 4D. The strange distortions are artifacts of projection, not the object itself. By studying these shadows, mathematicians deduce properties of 4D shapes, counting vertices, edges, and faces. We're like Plato's cave prisoners, inferring the true forms from their shadows. Projection is our bridge to 4D geometry, letting us build mental models of what we can't see. It's how we reason about the invisible. How does all of this connect back to the complex numbers we've been exploring? It might seem like a leap, but the connection is surprisingly elegant and profound. We're about to see how complex numbers are just the beginning of a much larger, more intricate mathematical structure. The 2D complex plane, with its real and imaginary axes, is just the starting point. It's a foundation upon which we can build more complex and fascinating mathematical ideas. Back in the 1800s, the brilliant mathematician William Rowan Hamilton was wrestling with a similar question. He was determined to extend complex numbers into the realm of 3D space, hoping to find a way to represent rotations and orientations in a more natural way. But the math just didn't seem to cooperate. He faced roadblock after roadblock, and his initial attempts to create a consistent 3D number system were met with failure. That is, until he had a flash of insight, a moment of pure mathematical inspiration. He realized that the solution wasn't in 3 dimensions at all, but in the seemingly impossible realm of 4 dimensions. This led him to invent quaternions, a new kind of number that would revolutionize mathematics and physics. Quaternions are numbers that have one real part, just like complex numbers, but they also have 3 imaginary parts, denoted as I, J, and K. These imaginary units are all perpendicular to each other, forming a 4-dimensional space. Now, quaternions don't behave quite like the numbers we're used to. They follow a set of very specific and somewhat unusual multiplication rules. These rules state that I squared, j squared, and k squared all equal -1. And when you multiply I, j, and k together in that order, you also get -1. A seemingly strange set of rules that govern how these imaginary units interact. And perhaps even more surprisingly, multiplication with quaternions isn't commutative. This means that the order in which you multiply them matters. In general, ij is not equal to g. This non-commutative property might seem strange, but it turns out to be perfectly suited for representing rotations in 3D space, where the order of rotations also matters. In essence, quaternions are 4-dimensional numbers, and they represent a direct and natural extension of the complex number system. They take us beyond the familiar 2D plane and into a higher dimensional space. Just as a complex number can be visualized as a point on a 2D plane with its real and imaginary coordinates, a quaternion can be thought of as a point in 4D space, defined by its real and 3 imaginary components. Therefore, when we envision complex numbers within the context of 4D, we're essentially seeing them as a special case of quaternions, where the 2D complex plane exists as a particular slice or subspace within the larger 4D quaternion space. The world of numbers and the mathematics they unlock is far more expansive and intricate than we might initially believe. It's a universe of endless possibilities waiting to be explored. Quaternions are fundamental in computer graphics and robotics because they elegantly describe 3D rotations. A quaternion lives in 4D, but it rotates objects in 3D without the problems of other methods. To rotate a vector, we use quaternion math, sandwiching the vector between a quaternion and its inverse. All rotation quaternions have length 1, forming a 4D hypersphere. Every point on this hypersphere represents a unique 3D rotation. When an airplane twists through the sky, its orientation traces a path on this 4D surface. We can't see the hypersphere, but we see its effects in our world. Quaternions are the hidden 4D mechanism behind every 3D rotation we observe. To navigate 4 dimensions, we need new geometry hyperspheres and hyperplanes. A hypersphere is the 4D version of a sphere. All points a fixed distance from a center. We can't picture it, but we can understand it through 3D cross-sections, spheres that grow and shrink. A hyperplane in 4D is a 3D slice. Imagine our universe as just one hyperplane among many. These ideas aren't just abstract, they're tools in data science, where high-dimensional spaces help classify and analyze data. Thinking in 4 dimensions is like learning a new sense. Awkward at first, but powerful with practice. We reason about intersections, projections, and relationships, seeing with our minds. This is the art of exploring invisible worlds. Computers extend our minds into 4 dimensions. Through code and graphics, we create visualizations that let us see 4D space. One trick, use color to represent the 4th dimension, mapping values to colors on a 3D object. Another, stereoscopic projection, showing 2 3D shadows of a 4D object, one to each eye, hinting at 4D depth. These tools let us interact with and build intuition for higher dimensions. We rotate, project, and experiment, turning abstract math into tangible experience. It's the closest we get to feeling the 4th dimension. Our journey from the 2D complex plane to 4D quaternion shows the mind's power to reach beyond its senses. We started with shadows and inferred a richer reality. Numbers have hidden depth, a secret life in spaces we can't visit, but can map with math. Higher dimensional thinking reshapes our view of reality, revealing order where there seemed only confusion. Quaternions make 3D rotation simple and elegant. The fourth dimension was discovered in the mind, not the lab. By playing with shadows and cross sections, we build intuition for the invisible. Stretching our minds to these abstract worlds, we glimpse the multi-dimensional beauty woven into reality. If this journey expanded your mind, imagine what the next one could do. Like this video if you felt that spark of curiosity. Share it with someone who thinks math is just numbers. Show them it's a language of dimensions. Drop a comment below. What part of this dimensional journey challenged or inspired you the most? And if you haven't already, subscribe to the channel. Because this is just the surface, and we're diving deeper every week.